What sets hockey apart from other sports is just how many different ways a player can pass the puck to their teammates. But how can this be mathematically captured, just like other stats have been for a century? In this work, we build a model to identify different types of passes in puck and player tracking data, and mathematically model different passing lanes available to a player. I'm David Radke, a PhD candidate in computer science at the University of Waterloo. This is work completed with my co-authors Tim Brecht and Daniel Radke, titled Identifying Completed Pass Types and Improving Passing Lane Models. The dataset we use in this work is the recently collected NHL puck and player tracking data. Tracking technology is located on each player and inside of the puck. Player locations are sampled 12 times per second and the puck 60 times per second. Locations are recorded in 3 dimensions with X, Y, and Z coordinates, and the origin is located at center ice. The tracking data comes with event labels, which signal the timestamp of an event such as a pass, shot, goal, and many more, and the identities of the players involved in the event. We previously published work in the AI for Sports Analytics workshop at IJCAI last summer, where we developed various metrics around passing and pressure from other players. In the paper I'm presenting today, we present a model to identify different types of passes and extend the passing lane model from that initial paper. We previously identified a passing lane as the available space between a passer P and receiver R, and identified that a passing lane should always assign a real numbered value, incorporate the area surrounding the passer and receiver, be asymmetric with respect to the pass direction to account for possible reaction times and sticks, and scale with respect to pass length. The size and shape of the passing lane is determined by a single parameter gamma. To show how the passing lane fits to the locations of players, consider this scenario with a passer, receiver, and 2 opponents. When gamma is 0, the lane is just the direct line between P and R. We grow the value of gamma until it reaches an opponent. In this case, the lane contacts opponent 1. The corresponding value of gamma is then the passing lane value. While a good initial model, there remains several limitations, such as only modeling direct passes and treating players as static objects. Our first contribution of this work is to identify different types of passes in the tracking data. The event dataset only contains labels for a pass and not what type of pass was made. We identify 4 different classes of passes. First, direct passes from P to R, rim passes where P rims the puck around the corner boards, and one-bank passes where the puck is banked off a straight section of boards. And a 4th class other, which includes various edge cases beyond the scope of this paper. Imperfections in puck locations or pass beginning and end timestamps make identifying each type of pass incredibly difficult. First, we identify direct passes as those which do not have any points within 2.5 feet of the boards. We chose 2.5 feet through observations, although we'd like to learn an acceptable threshold directly from data in future work. Since direct passes can also happen close to the boards, we also project the 5 possible ways for P to pass the puck to R, omitting corners and lanes through nets. If the pass with the least point-wise Euclidean distance error is the direct lane, the pass is also classified to be direct. Next, from the set of remaining passes, we classify rim passes as those with greater than 3 direction changes larger than 4 degrees close to the corner boards. We chose a threshold of 3 due to the one-bank passes described next and used the same 2.5 foot boards buffer as before. To classify one-bank passes, we leverage the unit circle from trigonometry. A one-bank pass, which typically bangs off the boards, will have 3 consecutive location points before and after the contact, such as PIA, PIB, and PIC, shown here on the left. The movement vector shown in red is moving at about 60 degrees located in quadrant 1 of the unit circle, which we show on the right. After contact, the movement vector would traverse the 90-degree threshold and then be located in quadrant 2. If 3 or fewer points are involved in a traversal over the quadrant thresholds of a unit circle, the pass is classified as a one-bank pass. In this example, these 3 points would be PIA, PIB, PIC, and the traverse threshold would be 90 degrees. Our next contribution is to extend the previous passing lane model to include one-bank passes, since it was only able to model direct passes previously. Our solution consists of modeling the one-bank pass as a direct pass through the theory of geometric reflections, ignoring things like spin or energy loss due to board contact, and then calculating the passing lane using all real and reflected opponents. To visualize this, consider this example in the neutral zone. The direct passing lane is modeled to be basically non-existent. However, P can make a one-bank pass to R, which is more open than this direct pass. To model this, we reflect the ice surface about the boards, including all potential receivers and opponents shown here. We can then approximately model the passing lane as a direct pass with regards to all real and imaginary opponents on the ice. For example, I'm unable to make this direct pass to my teammate. But if I consider indirect passing lanes, I can make a clean pass to my teammate with less risk of interception. Our second extension to the passing lane model includes the expected movement of all players. To do this, we utilize players' velocity at the time the pass is made and the expected duration of the pass based on machine learning from previous passes and various lengths. Now consider this example. The previous model would associate this scenario with a huge passing lane regardless of however these players were moving. However, P is likely to pass where R is going to be, instead of where they currently are when they're making the pass. So we project R to where they would likely be using their location, expected duration of this pass, and their current velocity. Opponents are also moving, but should only be projected until the puck passes their perpendicular location, since they can't really interfere the pass after the puck has already passed them. Thus, we calculate the expected time for the puck to reach this dotted line and only project the opponents that far into the future. We then fit the passing lane using these projected locations instead of the player's actual locations. In this example, I pass to where my teammate is expected to be while also considering where the opponent will be, resulting in a completed pass and a goal. If I didn't account for the expected movement of all players, such as our previous model, I would have ended up with a very different result. From this angle, you can see how large the passing lane would be given our previous model. However, our new model considers this lane to be smaller, and attempting this pass results in disaster. We analyze our models on 198 NHL games from November of 2021. We leverage the tracking data and previously labeled pass events in the dataset. We find that 84.4% of passes in our dataset are classified to be direct. 10.2 are one bank, 2.6 are rims, and 2.8 are other. In our dataset, while forwards as a whole pass slightly more than defense, considering there are typically 3 forwards and 2 D, a defensive player on average completes 43% more passes than a forward. We parse the locations of one-bank passes by D and forwards, shown in the bottom figures. We find that D tend to make one-bank passes behind their own net and off their own half walls, while forwards typically make one-bank passes behind the offensive net and off the offensive half walls, likely back to the D. Since we can now model passing lanes for one-bank passes, we propose a new metric called the gamma ratio, which is the gamma for the direct passing lane over the gamma for the indirect passing lane for the pass that the player chose. Thus, if the gamma ratio is less than 1 for for a one-bank pass, the indirect lane was bigger than the direct lane. Otherwise, the direct lane was actually bigger. We find that players chose to make the indirect pass when the one-bank lane was bigger in 59% of one-bank passes in our dataset. For an in-game example, consider this scenario. At time t on the left, player 86 has possession of the puck. Our previous model would consider number 28 to be the most open, the right defenseman. However, our new model suggests that the one-bank pass back to number 3 is the most open. This ends up being the pass that 86 made and has a gamma ratio of 0.5. Completing this pass actually increases the passing lane to 86 from 0.3 to 0.98 in the right figure. This series of passes on the power play is called an up and over and is a common play with the man advantage. This is what an up and over looks like in video. The indirect pass up the wall would circumvent the defender and open up the D-to-D pass. The rest of the clip shows typical power play movements and formations, ending with a goal. Finally, we find that our model of expected movement reduces the error in receiver location in 94% of passes, and sometimes up to 5.2 feet. We would like to highlight various potential applications of our models at different levels of the game. For fans, our passing lane model could enhance broadcasts or augmented reality views to highlight the most open player or gamma value, as shown in this figure as an example. For coaching and reviewing video, our models could provide quantifiable impacts of positioning and movement for both offensive and defensive situations, and allow coaches to manually adjust the positions of players to study what their positioning could actually do to the available passing lanes. And for general managers, since watching every second of a potential prospect isn't feasible, our models could help quantify passing behavior in a game or across a season and provide insights into player skill or passing trends. We do acknowledge that our work still has several limitations. First, our dataset did not contain any data for incomplete passes. Therefore, our results may not be reflective of all passing behavior, and inaccuracies in the tracking data timestamps may impact our results. Future work hopes to involve gaining access to a dataset of incomplete passes and finding correlations between gamma values and pass completion probabilities. A natural extension of this work is to next model the passing lane for rim passes, and to include more advanced or realistic models of expected player movement, such as ghosting or physics-based models typically used in soccer. Finally, this work would not have been possible without our collaborators and people who helped out along the way in making this paper. Thank you.